Hello class, here is section 7.4, chords and arcs. So let's take a look at how this goes. And our objectives are to use congruent chords, arcs, and center angles, and to recognize properties of the lines through the center of a circle. Those are the objectives of this particular lesson. Let's take a look at our first definition. A segment whose endpoints are on the circle is called a chord. And a chord, as you can see on the diagram here on the right, we have chord PQ. And if you notice, P is on the circle right here, and Q is on the circle right there. So notice that the chord does not go through the center of the circle, though the diameter is a type of chord. Under general circumstances, we do not call the diameter a chord, we just call it diameter. All right, moving on to our first theorem, we have theorem 7.8. And theorem 7.8 says, within a circle or in congruent circles, congruent central angles have congruent chords have congruent arcs have congruent central angles. That's what it says. And let's take a look at some examples dealing with exactly that. I'm going to bring this over here so we can work on it. And it says, in the diagram, circle O is congruent to circle P, given that arc BC is congruent to arc DF. What can you conclude? Well, first of all, it says that the two circles are congruent. And if arc BC is congruent to arc DF, we can say that chord BC is congruent to chord DF. And we can also say, we can say that the central angle BOC is congruent to angle DPF. And there we have that. That's based on theorem 7.8. If the two circles are congruent, and given that the arcs BC and arc DF are congruent, that's what we can actually conclude. Okay, part B is yours to do. So after I read it, pause the video and see if you can come up with the same conclusion as I do. Here goes. If you are instead given that chord BC is congruent to chord DF, what can you conclude? All right, let's take a look. So back again, we can say that if chord BC is congruent to chord DF, then we can say that arc BC is congruent to arc DF. All right. We can also say that angle BOC is congruent to angle DPF. And since we have all that, we can now say also that circle O is congruent to circle P. All those we can conclude, assuming that that's all they gave us. All right, moving on to the next thing. Theorem 7.9. Theorem 7.9 states, within a circle or incongruent circles, chords equidistant from the center are congruent. And number two, congruent chords are equidistant from the center. So essentially, applying that to the diagram, I'm going to take number one, for instance, and be more specific. All right, so for number one, chords equidistant from the center are congruent. So essentially it says if chords are equidistant, so that means if OE, segment OE right here, is congruent to OF, then the chords AB and CD are congruent. Then AB is congruent to CD. That's what number one says, assuming that we're in the same circle. Number two says congruent chords are equidistant from the center. So number two in the diagram would say that if chord AB is congruent to CD, chord CD, then they're equidistant from the center. So that would mean that OE will be congruent to OF. That's what this theorem actually states, applying it to the diagram over here on the left. All right, let's take a look at some examples. Okay, it says find the value of A in the circle on the right. So here's our circle here on the right. We are given that PQ is 12.5. We are given some measurements here. Over here we have a 9. A 9 over here. We need to find the value of A. So here's what we know. We know that the distance from the center to PR right here is 9. Right here, right? We also know that the distance from the center to this other chord over here, we have two chords, one calls PR, the other one doesn't have much of a name, but is actually, let's call it A. This chord A right here is also 9 units apart. So if we go back to the theorem that we just talked about, it says that if two chords are equidistant from the center of a circle, then they're congruent. So that means that PR is congruent to A. So we have that 12.5. This piece right here is 12.5. So that means that the other piece is also 12.5 over here. So this is also 12.5. Notice that they're congruent. It tells you right there in the diagram. So this guy here is 12.5. So that means that 12.5 times 12.5 gives me that PR equals 25. And we know that PR is congruent to A. Therefore, that means that A equals 25. All right, that's basically what the theorem stated. So since the two chords were equidistant from the center, they are also congruent. So that's where the 25 comes from. All right. Part B is yours to do. So I'm going to read it. I'm going to pause pause the video and then you can actually see if you get the same answer I do. So find the value of x in the circle on the right. Very good. So give this some thought and see if you get the same answer. All right, let's take a look. So right off the bat, we can see the two chords. We have the full measurements of the chords. This chord right here, is one piece is 18, the other piece is 18. The full length adds up. 18 plus 18 is 36. So we know that this length over here is 36, and so is this one, 36. So since the two chords are congruent, meaning they both measure 36, then that means that the distance from the center of the circle happens to be the same. We know that the distance of this one is 16. So if this distance is 16, then x is also 16. X is 16. So that's that one problem right there. Moving on to the next thing, we have theorem 710, 711, and 712. And they go like this. In a circle, a diameter that is perpendicular to a chord bisects the chord and its arcs. In a circle, that's theorem 711. Now it says, in a circle, a diameter that bisects a chord, it's perpendicular to the chord. And theorem 712 states, in a circle, the perpendicular bisector of a chord contains the center of the circle. All right, one term that I want to review a little bit is perpendicular bisector. A perpendicular bisector is when two lines, segments, or rays happen to intersect. They actually, let's say, for instance, I have this is A, B, this is C, and this is D. If DC happens to be a perpendicular bisector, two things happen. The intersection happens to be 90 degrees, and then the distance from A to C and from C to B happens to be congruent. So that is what a perpendicular bisector is. So we're looking for this kind of relationship. So that means that CD is a perpendicular bisector. Perpendicular bisector. All right. So let's take a look at how we can apply all these on our next examples. Okay, here we have this. Find each missing length to the nearest tenth. To the nearest tenth. So here we are trying to find the radius on the first one right here, R. Now it tells me that the length from K to N is 3 centimeters. It tells me that the chord LM is 14 centimeters. If we go back to what the theorem states, that means that KN intersects my chord at a 90-degree angle. So the little triangle that we have here, formed over here, this little triangle is a right triangle. We have the base, we have one side. That means that R is my hypotenuse. So we can actually use the Pythagorean theorem to calculate this. So we would actually say that R squared equals, and I'm just going to write this first in general terms and then we'll actually plug in the numbers. So that means that we have ln squared plus nk squared, nk squared. All right. So now we go substitute. We're looking for r, so it's r squared. Ln happens to be, was not 14. Ln is half of 14 because, well, this right here, if it's perpendicular, that means that it bisects my chord. So it is half of 14. So in this case, we're going to have that Ln is 7. So it's going to be 7 squared. Let me actually make that squared plus nk. And nk is 3. So it's going to be 3 squared. So we have r squared equals 49 plus 9, which we have r squared equals 58. And now it says to the nearest tenth. So we need to actually take the square root of both sides. So we have r equals the square root of 58. And the square root of 58 is equals to 7.6156. To the nearest tenth, this is approximately equal to 7.6. And our units of length happens to be centimeters. So we would say centimeters. And that's our answer right here. Okay. So now for number 2. Number 2, notice that it tells me that from A to C is 11, and from C to this point over here, which I'm just going to call it D, from C to D is also 11. So if this distance right here, if that means that CB is a midpoint, or actually point C is a midpoint. So because from C to B, I'm going through the radius, then that means that this angle right here is 90 degrees, because this segment, if this point is the midpoint, point C is the midpoint, and from C to B, I'm actually on the radius of the circle, then this angle right here is 90 degrees. If it's 90 degrees, now the little triangle here where Y is a right triangle, and we can calculate that using the Pythagorean theorem. So we now have that 15 squared equals 11 squared plus y squared. So 15 squared is 225. 11 squared is 121 plus y squared. So then we take 121 from both sides, and we get that y squared is 104. Then we take the square root of both sides, and we get that y equals the square root of 104. And that gives me that this equals 10.198. So to the nearest tenth, this comes out to be approximately equal to 10.2. And we are not given units on this, so we just leave it at that, or we can say 10.2 units. Since we're dealing with lengths, if the unit is not specified, we just put units, 10.2 units. All right, that is that one problem. Now let's take a look at this one. This one is for you to do. I'm going to read it and then you may pause the video to see if you can work it out and then see if you get the same answer that I do. So it goes, use the circle at the right. Find the length of the chord. And 2, find the distance from the midpoint of the chord to the midpoint of its minor arc. All right, good luck. Okay, so let's try to do number 1. So number 1, it says find the length of the chord. So I'm trying to find the length of the chord. So if you take a look on the diagram, x happens to be on the radius of the circle, right? So if it's on the radius of the circle, that means, notice that it's also 90 degrees. So if it is 90 degrees, x therefore is the midpoint of the chord down here. If it's the midpoint, right? If it's the midpoint of that chord, that means that this length right here is congruent to the length right here. So I can actually say that this length right here, if the full length is x, then half of that is half x. So I'm going to use that. So the Pythagorean theorem, which is what we can actually use on here, would say that 6.8 squared, 6.8 squared equals 1/2 x quantity squared plus 4 squared. I use 1/2 x, remember, because the full length of the chord is x, and since it was bisected, half of x is 1/2 x, which is what we put over here for this little length over here. Okay, so now we go ahead and square each of those. So we have 6.8 squared happens to be 46.24. 46.24. That equals 1/2 squared happens to be 1/4 x squared plus 16. So now we move the 16 to each side by subtracting it. So we subtract 16, and we get that 1/4 x squared equals 30.24. 30.24. Now I want to get rid of that 1/4. So the way to get rid of this 1/4 is by multiplying it by this denominator of 4. So we multiply both sides by 4. The 4 over here goes away, leaving me x squared. And 30.24 times 4 is 120.96. That's the value for x squared, but I'm not interested in x squared. I want to know what x is. So I take the square root of that, and we get that x equals the square root of 120.96, which equals 10.9982. Since it doesn't tell me how many significant digits to actually do so, I take a look at the values that I'm given. This one doesn't have one, but this one goes to 6.8. So I'm going to go to one significant digit. So when I go over here, this goes 10.998 to the nearest tenth. So this actually becomes approximately 11. 11.0. And yes, we actually put the 0 because 0 is my decimal place. So 11.0, and we don't have any units. Since we're dealing with length, that will be 11.0 units, and that's how much x is. All right. Now, we need to find out now for number 2, and I'm just going to scroll over here and do number 2. Number 2 now says, find the distance from the midpoint of the chord to the midpoint of its minor arc. The minor arc is right here. I'm just going to go around it so I can point it. This arc is the minor arc they're talking about. So they want to find out what the distance is from here to here. So that is hopefully as clear as you can see. Notice that the full radius is 6.8 and the distance from the radius to the chord is 4. So that means that the distance we're looking for is the difference between the two. So we have 6.8 minus 4. So we have 6.8 minus 4. That gives me the answer to be 2.8. And that is the distance from the chord to the from the midpoint of the chord to the midpoint of the arc. All right. And that is it for this lesson. If you have any questions, feel free to send me an email or we can actually talk on Teams. Have a good one, and we'll see you next time.